How we do in AP Statistics? We are in section 2 of chapter 11. We're going to talk about types of samples, starting with the gold standard of good sampling, the SRS, or simple random sample. A simple random sample, often abbreviated SRS, is the ideal sample. It is a sample in which every subject of the population has an equal chance of being selected. But wait, there's more. Every possible combination of subjects has an equal chance of being selected. So not only does every subject of the population have an equal chance of being selected, but every possible combination of subjects, any possible grouping of subjects, has an equal chance of being your sample. Here is a non-example. All right, so this is not a simple random sample. Suppose we want to learn about the employee satisfaction at some creatively named restaurant called Burger Hut. We assign each location a number and choose 3 numbers. Okay, so we got 3 locations. Then we sample from those 3 locations to generalize about employee satisfaction in all of those locations. This, by the way, is not an example of simple random sampling because it is a cluster sampling technique. We will learn about it later. But what is it about this non-example that makes it not a simple random sample? Well, notice that not every possible combination of subjects is selectable with this model. A sample chosen with this model cannot be a simple random sample. Since we are choosing 3 numbers and thus 3 locations, we cannot sample people from more than 3 locations. That means that say we had a sample of, say, 50 individuals. Those 50 individuals can only be from 3 locations. They can't be from 1 or 2 locations. That would be rather silly. But they can't be from 10 or 20 different locations. They can only be from 3 different locations, which means that not every possible combination of subjects has an equal chance of being selected. So, as you can imagine, a simple random sample is a high standard. It's a lofty goal to reach. Not only to have every subject of the population have an equal chance of being selected, but every possible combination of subjects needs to have an equal chance of being selected. So here's how we select a simple random sample. First, we need to define where the sample will come from. The sampling frame is the list of subjects from which the sample is drawn. So, for example, to select a simple random sample of college students, we could obtain a list of all the registered students and sample from that list. As you can imagine, the larger the sample frame, the more the sample frame is precisely to the size of the population, the better the sample we will get. And if that sampling frame does in fact contain every member of the population with all the information that we would be looking for, then we stand the chance of selecting a simple random sample. So in this process, we will define the population we're dealing with. So going off the prior example, are we concerned with only full-time students, if we're talking about the college, full or part-time students, only on-campus students, on-campus or commuter students? We need to define what population we are dealing with. We could try and do a study on all students, but there are many different kinds of students. Maybe we want to focus more on the full-time on-campus students, or just the commuter students, or students who are enrolled full-time, whether they are commuter or not, or maybe just part-time students. Maybe we want to narrow our focus a little bit, and that'll increase our chance of getting a simple random sample, because it's not easy to do. Once we choose our sampling frame, we can assign a random number, so there's that randomness from chapter 10, to each individual and use any of the methods we've discussed to choose random numbers from the list, however many we need. And though each sample we choose will vary a bit from all the others, every sample we could choose is going to be different, and thus the numbers are going to be a little different when we learn about the sample. The more random the sample, the lower the sample variability will be. So we're going to learn how to quantify sample variability later this year, but spoiler alert, you want sample variability to be as low as possible. Remember that last video when you saw two samples that were almost identical with only small differences between the statistics between those two samples? That demonstrates small sample variability, which means the sampling technique we're using is good. So here's an example from your book about selecting a simple random sample using some random numbers. So there are 80 students enrolled in an introductory stats class. You are to select a sample of 5 of them. So here's the question. How can you select a simple random sample of 5 students using these random digits found on the internet, the source of all truth and wisdom? So here is a set of random numbers, a couple bars of random numbers, if you will. Think about how you would use these random numbers to select 5 students. This is a good review of Chapter 10 content. Feel free to unpause the video when you are done. All right, let's look at the answer, also provided by the textbook. So first you can number the students from 00 to 79. All right, that's 80 students if you start at 00. Taking the random numbers 2 digits at a time gives me 05, 16, 62, 93, 05, 77, and 48. And here's 2. Guess you can't use that. We'd need to know what number's next to it. So you ignore 93. There is no student number 93. And so as not to pick the same person twice, I'll skip the repeated number of 05. So we have a 05 in the beginning, and then later on we have a 05 again. Well, that's inconvenient. We're going to ignore this 05 and just proceed on to the next value. So my simple random sample consists of students with the numbers 05, 16, 62, 77, and 48. That's how we would use a table of random numbers found on the internet to select some students at random. Here are some other sampling designs. Now, the simple random sample is more or less the gold standard, but there are other designs that we can use in special situations or in situations where a simple random sample would just be too difficult to attain. In addition to a simple random sample, there are several other designs that statisticians use to sample from a population. We could talk about stratified sampling, cluster sampling. Now, those two styles of sampling are, they sound similar at first, but there are key differences, and I will do my very best to make sure you clearly know the difference between stratified and cluster sampling. There's also systematic sampling. So let's talk about stratified sampling, featuring our 2 favorite animals here on this election year in which I'm filming this lesson. Yeah, the slide's a little on the nose. When we think of different groups in the population, and we suppose that they're going to have different responses or outcomes depending on which group you're in, we can reduce sampling variability by essentially forcing our sample to resemble the population. For example, if the population of a town consists of 55% Republicans and 45% Democrats, an opinion poll meant to sample 100 people could be administered to a simple random sample of 55 Republicans and another simple random sample of 45 Democrats, rather than a simple random sample of the 100 people and whatever Republicans and Democrats we get. So a simple random sample of any 100 people could consist of 55 Republicans and 45 Democrats. It could consist of 60 Republicans and 40 Democrats. It could consist of an even split or any other combination you can conceive of. But a stratified sampling technique would force this 55-45 proportion to hold in our sample. 55% Republicans, 45% Democrats. Well, of the 100 people, we want exactly 55 Republicans and exactly 45 to be Democrats. Now, Why isn't this a simple random sample? Well, this means our sample is not a true simple random sample because not all possible combinations of subjects are sampleable, if that is in fact a word. In other words, we can't have a sample that consists of 50 Republicans and 50 Democrats if we are forcing our sample to consist of 55 Republicans and 45 Democrats in accordance with the distribution of the population along the two major parties. Okay? So this is not a true simple random sample because there are combinations of subjects that are in theory sampleable that we couldn't sample if we were using the stratifying technique. However, a stratified sampling technique is actually debatably better than a simple random sample in this particular case, because even if we don't know whether the two parties will disagree, stratified sampling eliminates the possibility of sampling variability being unnecessarily large. If we were to select 100 people and we got an even split of Republicans and Democrats, and in our next sample, we got 60 Republicans and 40 Democrats, yeah, the variability is going to be pretty big. But if we rig things so that we have 55 Republicans and 45 Democrats in accordance with their distribution in the population, and we do that every time we sample, yeah, that variability is going to be pretty small. These subgroups assumed to be different are called strata, and the type of sampling is called stratified sampling. So these Republicans and Democrats, we call those groups strata in this case. And if we sample from those strata in accordance with their distribution in the population, that is stratified sampling. So let's employ our stratified sampling technique. You're trying to find out what freshmen think of the food served on campus. By the way, if you haven't noticed, this textbook assumes that you're a college student, which is kind of cool. Food Services believes that men and women typically have different opinions about the importance of the salad bar. No comment. How should you adjust your sampling strategy to allow for this difference? Well, here's what the writers of the textbook say. One writer says, I will stratify my sample by drawing a simple random sample of men and a separate simple random sample of women. I'll be sure the two sample sizes are proportional to the overall college enrollment figures for men and women. So we think that men and women are going to put a different amount of importance on the salad bar. So we would want to sample from men and separately sample from women in proportion to men and women at the university. Now, this may change in the future, but this is important because at a lot of colleges and universities, there are more female students than male. So we want to make sure that our sample consists of proportionally more female students than men. So say the distribution at a college is, 53% female, 47% male. For every 100 people we would sample, we would want 53 ladies and 47 men. That's how we would stratify to limit our sampling variability. And those are our two strata. We have the men and the women, and we would sample in proportion to how they appear in the population. Now let's talk about cluster sampling. Cluster sampling is easily confused with stratified sampling, but there is a key philosophical difference that I hope you catch. When we want to study a large population in which we assume there will be no noteworthy differences in outcomes between the subgroups within the population, we can divide the population into representative clusters and gather a simple random sample of a few of them. Did you catch the big difference between stratified and cluster sampling? If you did, awesome. If you didn't, read on. So we will call this method cluster sampling. For example, if I were doing a study on the reading level of a book based on the length of sentences, instead of assigning each sentence in the book a number and having to find each sentence that you sample, which would take absolutely forever, I could divide the book into representative clusters of 5 pages and choose a few clusters, at random hopefully, and study those. This is a good example from our textbook about cluster sampling. I don't want to search the book for sentence number 5,207 or something, and then sentence number 506 or something like that. That would be awful. So we could break the book into clusters of 5-page intervals and sample from a couple of those 5-page intervals. That's a much more doable strategy. Let's talk about the difference between stratified and cluster sampling. Let's go back to stratified sampling. That's when we sample from the population in a manner that takes into account that groups will likely produce different outcomes. For example, Republicans versus Democrats, men and women, children versus adults, etc. And we achieve this by forcing our sample to resemble the population. We force our sample to abide by the proportions of Republicans and Democrats in the population, men and women on the college campus, children and adults in our town or city, etc. Why do we do this? We do this to narrow the sampling variability. We do this so that if we were to take multiple samples, there wouldn't be much variation between the samples. Cluster sampling. We divide a large population into clusters that we assume have about the same characteristics. For example, restaurants in a chain, classrooms in a particular grade, at school, etc. So that by sampling from a few, we can learn about the whole population. And we do this because sampling from large populations can be laborious. We are admittedly giving ourselves a break because a simple random sample is just too hard to come by. Our population is too big and too scattered. We want to make it a little easier on ourselves, so we cheat just a little bit and use cluster sampling. Notice the big difference. In stratified sampling, we divide our population into strata, which are groups that we assume are going to have different outcomes. We can look at a population divided along party lines or divided between men and women, children and adults, etc., and say, my population features groups that as a whole are going to produce different results than some other group. So we need to make sure our sample looks like the population to minimize our sampling variability. But with cluster sampling, we break the population into clusters, which are groups that we assume have about the same characteristics. That way, if we only sample from a few of those clusters, we can learn about all of them because of that assumption. So strata are groups in the population or divisions in the population that we assume will produce different outcomes most of the time. But clusters are groups of an especially large population we assume have the same characteristics. So by studying a few of those clusters, by choosing a few at random, say assign each cluster, each say restaurant in the chain, classroom in a particular grade at a large school, to a random number, select a couple random numbers. Okay, we got a couple restaurants, we got a couple classrooms, and now we're going to assign each member of those, the employees of the restaurants, the students in the classrooms. We're going to assign each of them a random number and sample from those handful of clusters rather than absolutely everybody in all the restaurant chains and all the classrooms. Yet again, the book has a great analogy when it comes to stratified versus cluster sampling. And it involves a Boston cream pie. All right, so if you don't know what that is, Imagine a Boston cream donut, but bigger. It looks kind of like that. Stratified sampling would be sampling bits of the icing, bits of the cake, and bits of the cream in proportion to their representation in the pie. So there's a little bit of icing on top, so you sample a little bit of icing. There's a bit more cream inside, so you sample a higher proportion of cream. And most of all, there is the cake itself, and so you would sample the highest proportion of cake. And that would give you an idea of what the Boston cream pie tastes like. Cluster sampling would be cutting out a slice of that pie that has all the flavors, which is representative of each other slice of the pie. So if I wanted to get an idea of how the pie tastes, I would cut a little slice out of the pie that I assume would taste about the same as any other slice of the pie. So that is a set of two strategies I could use to get an idea of how the Boston cream pie tastes. One that involves sampling proportional to the representation of the population, and another that involves assuming that each slice is going to taste the same as any other. Now that we have the difference between stratified and cluster sampling down, let's look at another example of cluster sampling. Suppose you wanted to figure out what proportion of students at Canaan campus buy pizza on Fridays. Now, you don't want to track down a bunch of randomly selected students from Canaan. That means an SRS would be too time-consuming, especially because you take AP Stat. But you assume each homeroom will have about the same proportion of students who buy pizza on Fridays. How could you use cluster sampling? Think about it for a moment, pause the video, and then unpause the video when you think you have a good strategy. All right, here's my answer. Compare it to yours. I could make each homeroom a cluster and assign each homeroom a number. I could select a few random numbers with my nifty graphing calculator's random no rep feature. We don't want to choose the same homeroom twice, now do we? And collect a simple random sample from only those randomly selected homerooms. This employs the principle of randomness, and it employs the principle of if we can assume each of the homerooms have about the same proportion as our prompt seems to suggest, then we can use that to our advantage. It's better to, if we can make that assumption, select a few homerooms and study them, then try to track down some randomly selected students going all over the school and essentially wasting our time when we could be studying for AP Statistics.